Hello again. This is Eric and welcome to Math from the Gut. In this video, we're going to consider how well the Pythagorean theorem scales. In other words, how is h, the length of our hypotenuse, affected when our legs x and y are both multiplied by the same number? For starters, what happens to h when both of the legs of our right triangle double in length? We'll start again with our 5, 12, 13 triangle. Watch how things change when we double x and y at the same time, like this. What do you think happens to h when we do this? Here, I'll do it again. One thing to notice is that the basic shape of the triangle stays the same. We still have a right triangle where one leg is more than twice as long as the other. Here's the original triangle. Our x length of 12 is a bit more than twice our y length of 5. The same thing can be said when we compare our new x length of 24 with our new y length of 10. Perhaps you can see from this alone that if the two legs double in length and we maintain the same basic shape, then the hypotenuse must also double in length from 13 to 26. But in case you're not convinced yet, I want to show you two other ways to look at this. First, we'll imagine a real test drive. Let's say that you're going down the highway and you see a sign shaped like our 5, 12, 13 right triangle, some distance away from you. Let's suppose that you stop the car, pull out a ruler, hold it at arm's length from your head, and look at the sign in the distance at the same time. When you measure the sign in this way, from a distance, you notice that the base of the sign happens to measure 12 centimeters. Now obviously the real sign is much larger than that. You only measure 12 centimeters because you're looking at it from a distance. In the same way, if a house is far enough away, it may only look a few inches tall, like you could hold it in your hand, even though it's obviously much larger. Next, before you start driving again, you measure the vertical side that goes up down in the same way and see that it measures 5 centimeters. Of course, the diagonal side, the hypotenuse of the sign, will then have to measure 13 centimeters at this point as we previously computed. Now, you start driving again towards the sign like this. Obviously, as you drive closer to the sign, all of its sides will appear longer. At some point, you'll be close enough that the x distance will appear to be twice as long. Let's stop the car there. Now, for the key point, when this happens, you're actually closer to all of its sides by the same amount. Because of this, all of the sides, including the hypotenuse, will appear to double in length. Notice again how we keep the same basic shape of the triangle when we double all of its lengths. Obviously, the sign needs to keep its same basic shape when we get closer, since it's still the same sign. For example, we won't suddenly turn into a circle or even a different shape of triangle just because we're closer to it. So, what happens is that when we're close enough for the x distance measured inside the car to double, we're also close enough for y and h to double as well. And our 5, 12, 13 triangle becomes a 10, 24, 26 triangle. So, when both of the legs double, our hypotenuse also doubles. We can also try this one final way. Again, let's start off with a 5, 12, 13 triangle. This time, let's put the length inside the triangle to keep things clearer later on. Finally, when I expand this triangle like before by doubling both x and y, keep an eye on the path that this blue dot takes. Here goes. Here it is again. Okay, so the question is how far over and how far up does the blue dot go? Now I know this is a bit tricky. Break it down. Think about where it starts and where it ends. Think first about how far right it goes and then about how far up it goes. You might want to pause and think about this for a bit. First, note where the dot starts. It starts out 12 over and 5 up from the left side of the triangle. Now, where does it end up? How far from the bottom left of the triangle is it after it has grown? Using the big triangle, we see that it is now 24 over and 10 up. So, overall, we've gone from the red dot to the blue dot. Measuring from this green dot, on the far left, we've gone from being 12 to the right to being 24 to the right. meaning we moved over an additional 12. We've also gone from 5 up to 10 up, meaning that we moved over an additional 5. So, to move from the red dot to the blue dot, we go over by 12 and up by 5. But that's exactly what our little red triangle already does, over 12 and up 5. So, what happens if we make an identical little triangle and place it so that it goes that extra distance from the red dot to the blue dot? We could do it like this. So the path mapped out by the legs of the small triangles is this. It makes sense that the second triangle should fit, since the two little triangles go a total across distance of 12 plus 12, or 24, and a total up-down distance of 5 plus 5, or 10. As you can see, the small triangles get us to the same place as the double-sized triangle does. The only difference is that these distances are split up a bit more than they are with the big triangle. Now that we hopefully see how everything fits, we can also see that the two hypotenuses of the small triangles go between the same points as the big triangle's hypotenuse. That is, from the green dot to the blue dot. In both cases, we go a total of 24 over and 10 up. Since the two little hypotenuses are both angled exactly the same, we see that together they form one line which is the same as the big hypotenuse. And we can get the length of that final line by simply adding together the two small hypotenuses for a total of 13 plus 13, or 26. To sum things up, putting the two small triangles together like this gets us to the same endpoint as the big triangle, and the total diagonal distance is equal to the combined diagonal distance of the two small triangles. In my opinion, this way of looking at things is a bit harder to see quickly than the previous way. Personally, I prefer thinking about where you get twice as close and everything, including the hypotenuse, gets twice as long. But it's always useful to see things in different, independent ways. Doing that strengthens our feeling that we're on the right track. Now, just to be clear, both legs must double in order for the hypotenuse to double. You can see here with this very wide but short triangle that the hypotenuse clearly isn't twice as long when we double only the height from 1 to 2, like this. The red h is just slightly longer than the blue h. So, what happens if both legs become 3 times longer? Hopefully you can see without further convincing that the hypotenuse must also become 3 times longer. So, in general, if we multiply both legs of a right triangle by the same factor, the basic shape stays the same and the hypotenuse must also grow or shrink by the same factor. So now, let's try and rattle the Pythagorean theorem a bit and see if it works as expected here. We start, of course, with the Pythagorean theorem and then substitute the numbers for a triangle that has legs of length 12 and 5 and do the math. That will be our original triangle. Next, let's see what happens with a triangle whose legs are double the length, in other words, 24 and 10. Plugging those numbers in, we get 26, or twice the value of 13. As you can see, when we double the 12 length to 24 and the 5 length to 10, then the hypotenuse doubles from 13 to 26. Now, let's say that our evil-minded or simply confused friend tells us that the Pythagorean theorem is h equals x squared plus y squared. In other words, he forgets to put the square root over x squared plus y squared. Let's start with a triangle whose two legs each have a length of 1. Plugging the numbers into this formula, we see that h equals 1 squared plus 1 squared, which is 1 plus 1, which of course equals 2. This is what we get for our original triangle. Assuming that we accept this as the correct answer, even though it isn't, let's see what happens when we double the legs to each have a length of 2. Now, plugging in the numbers, we see that h equals 2 squared plus 2 squared, or 4 plus 4, which equals 8. So instead of doubling like we expect, our hypotenuse has quadrupled or gotten 4 times longer. This happened because each of our squarings quadrupled things from 1 to 4. Since both the x and y portions quadrupled, the overall sum also quadrupled. So, on that basis alone, and the fact that a hypotenuse of 8 really makes no sense here, we can see that this formula is wrong, and that perhaps we shouldn't accept what our friend tells us, at least with regards to math, so quickly. So now, let's see if the doubling of the hypotenuse holds up when we start with a general right triangle with lengths of x and y. Remember that x and y can represent any numbers. Using the Pythagorean theorem, we get a hypotenuse of the square root of x squared plus y squared. So this is our original triangle. Next, let's try a triangle whose legs have doubled in length, in other words, 2x and 2y. Warning! We have a possible speed bump alert here. What follows is a bit more involved than what we've done before, so see if you can hang in there. Plugging those doubled values in, we get the square root of the quantity 2x squared plus the quantity 2y squared. Expanding each of these square terms, we see that this is the same as the square root of the quantity 2x times 2x plus 2y times 2y. Reordering our multiplications, we get the square root of the quantity 2 times 2 times x plus 2 times 2 times y, which can be written as the square root of the quantity 4x squared plus 4y squared. Distributing out the common 4 from both square terms, we get the square root of 4 times the quantity x squared plus y squared. Now, I don't want to get too sidetracked proving this, but hopefully you can see that we can separately square root the individual terms to get the square root of 4 times the square root of x squared plus y squared. One way to see this is to square this, and then square that, and after some reordering, convince yourself that their squares are equal. Finally, since the square root of 4 equals 2, this equals 2 times the square root of x squared plus y squared. Since multiplying a number by 1 doesn't change it, we can rewrite our original equation as 1 times the square root of x squared plus y squared. This allows us to more easily compare our results. Notice how in the first case h is 1 times the original length, but in the second case it's 2 times the original length. This tells us that when we double x and y, regardless of what they may actually equal, our result also doubles. Although I won't go through this step by step, the exact same algebra that we just used to double the legs of the triangle can be used to multiply the legs by any number, let's say c. If we do that, we get the following and discover that the hypotenuse also gets multiplied by c. So the Pythagorean theorem clearly passes our scalability test. If you give it some extra thought, I hope you can learn to see the scalability effect very quickly every time you look at the Pythagorean theorem. You should see how the overall scale factor gets squared under the square root sign, and then just becomes the scale factor itself when we pull it out from under the square root. We just have 2 test drives left. In the next segment, we'll see if there's some obvious lower limit for the hypotenuse. In other words, is there some meaningful value that the hypotenuse cannot be shorter than? Like robot Johnny Five said in the movie Short Circuit, input, give me input. So please, give me your input. I thrive on it. See you in part 7.